welcome back to calculus. We are getting something really big in calculus, even though this is merely a preview of calculus. Okay, we are in section 2.1. Three big things in calculus: limits, derivatives, and integrals. We are getting something really big in calculus. It's a derivative. Derivative is slope. Remember, this is what I said in the very beginning. Derivative is slope. And now I suppose you know, given a curve, okay, at any point there is a slope. The curve has slopes too. At any point there is a slope. And at different points the slopes are different. Okay, and then the way to find out the slope of a curve is we check with the slope of the tangent. And still, that's not easy thing at all. But we proposed to consider the slope of the tangent. We consider the slope of the secant. And also, I hope you understand the other big thing. The slope of the tangent, the approximation of the slope of the tangent can be improved by choosing a point closer to that given point. And indeed, we could, if we can handle the situation, indeed we can. And the calculus was invented, I think it's almost 400 years ago. Indeed, this way of arrangement, it simply works. It works perfectly. This is exactly how we handle derivative. Okay, we can improve and we get precisely the slope by choosing the point really close to that given one. Really close to that given one. We get the slope of the tangent. And the slope of the tangent, no doubt, it is the derivative. And the process, you move one other point very close to that given one, it is a limit process. So indeed, we are really getting two things of calculus already, limits and derivatives. Certainly, there are a lot more work to consider limits and derivatives. But put in a simple way, I say we got some idea started already. It's about limits and derivatives. Limits and derivatives. How about let's take a quick look about this function here, the parabola, x squared. The parabola, it is right here, the chart, there's the chart, there's the chart. Okay, so what I'm trying to do here is, by the way, this is really the example from textbook, example 2.1. It is to estimate the slope of the curve or slope of the tangent at a equals 1 for the squaring function. It is about this situation here, right here. X equals 1 and accordingly y equals 1, 2. I'm seeing a tangent line here. And also, before I do any calculation, I say at least I can tell the slope would be positive, right? Because two things. Overall, the pattern of the curve is going upward, and the tangent is going upward too. So the slope must be positive. And then, in the actual calculation, this is what I did. We are considering the situation at a fixed point, x equals 1 or a equals 1, and y is also 1. Y is 1 squared, y equals x squared. So that's 1 again. Okay. And we understand that to consider the slope of tangent, we can choose a point not too far away. So I consider x equals 2, which is not too far away. X equals 2 right here, not too far away. So accordingly, f of x equals x squared. And using the raw formula for the slope, rise over run, I did my calculation. I figured out the slope, that's 3. And indeed, it may make sense. You look at the graph of the parabola here. It's going upward. I think, well, 3 may make sense. Okay, might be, if you really have no idea, it might be a reasonable answer to give. Okay, but we also understand we can make the approximation better by choosing the other point closer to this one here. So my next choice is to take x as 3 over 2, 1.5, which is closer to 1, right, compared to 2. And then accordingly, when x equals 3 over 2, x squared, that's 9 over 4. And also I did a calculation for the slope. Slope, it is the same formula, rise over run. Keep in mind, a is fixed. X is changing, right? I'm choosing different x values according to the rightmost column here, okay? And then I got the slope at 2.5. So what I really want to say, even though I did just 2 calculations, I hope you agree with me. Between 3 and 2.5, 2.5, it is a better approximation of the slope at this point here. 2.5, it is a better approximation. Because the point we got, it is closer to this actual 2.1 here. And then if you are convinced, as I'm saying, I'm continue to choose points closer to 1, 5 over 4, 1.25. So it is closer to 1 compared to 3 over 2, 1.5, 1.25. And then I did a calculation. I see the slope turns out to be 2.25. Same formula, okay. I continued my calculation. I'm taking this time 1.1. It's harder to see the difference on the graph, but anyway, mathematically still it is very possible and very reasonable, very easy to achieve that. And then I figure out the slope turned to be 2.1. And I did also some other calculations. I could do more. What I figured out here is as I am at this fixed point, and then I choose the other points, getting closer and closer to this fixed point, I'm getting better and better approximation for the slope. And starting from 3 to 2.5, 2.25, 2.1, 2.01, and indeed I figured out I really don't expect I get anything about 1 point or something. Really, it will have to be a little above 2. Or indeed, if you push really hard, it's getting really close to 2, close to 2. So from this table of the calculation, I want you to know I am seeing 2 things. I am seeing 2 things, okay. Okay, this is the slope formula, rise over run. I have a fixed. X is chosen as those values getting closer and closer to 1. And as x is getting closer and closer to 1, the slope, it is getting closer and closer to 2. So that process, it is a limit process. We write limit as x approaching to 1, the slope, rise over run. And specifically to this expression here. This expression has a limit, which is 2. Remember in calculus, we study limits and the derivatives. So this is the first thing I want you to have some idea. We have the idea of limit already. The process showed on this table and the result I observed here. It is a limit process, and the entire calculation somewhat mathematically simply can be represented by this kind of writing. It is a limit. And also for this specific limit, it is for the slope of the tangent line at this 1. Okay, certainly we could always call this a slope of tangent, slope of curve, or simple slope. But anyway, it has applications more than slopes. Well, it's about rate of change, and it is the instantaneous rate of change. So we call that particular limit, this 2 here, simply it's a slope. But anyway, we give a more general term. It shows more than slope. We call this a derivative. And we write f prime of 1, which is derivative of this function at 1, which is 2. And another statement of derivative. Derivative is limit, and it actually could be a slope, or more importantly, it could be it should be it reflects the instantaneous rate of change. So this is the very beginning of Calculus 1. Very beginning of Calculus 1. I want to thank you very much for taking this class with me, and hopefully we will make it through for the semester. Thank you for watching.